working on at the same time, we've been working in the deep offshore Gulf of Mexico with a company called ION Geophysical, and they shoot long seismic lines that penetrate very deep, and you can see the entire crust. So I will try to integrate what we've been doing in the onshore and in the offshore. This talk will be all about plate tectonics and the evolution of the basement. There's not very much discussion of sediments, so it's really just how the basement came to be the way it is. Okay, we have known basically how the Gulf of Mexico evolved for a long time. These maps were drawn in 1999, so they're 22 years old already, but they're still pretty good. So we have the present day shown here on the bottom. And the first thing we want to do when we try to figure out the evolution of the Gulf, we need to close the oceanic crust, because that's the last thing that happens when you form a basin. First, you stretch or rift the crust, and then you start seafloor spreading to make some ocean crust between the two conjugate margins. So depending on how you map the occurrence of the ocean crust, you will get different reconstructions of Yucatan and the United States. So we'll talk about that. This is one possibility where Yucatan has been rotated up toward Texas. And so this map here shows all of the oceanic crust is gone. And then the next thing we need to do is to push Gondwana and North America back together more closely in order to bring everything back to how it was in the days of Pangaea, when all of the continents were together. So we have two primary steps going forward in time. First, we have the rifting history, and that involved northwest, southeast extension. And then that produced this reconstruction. And then the second stage is to rotate the Yucatan block down to its final position. And that second stage makes the oceanic crust. Okay, so what have we learned in the last 11 years? We have learned that we can constrain the spreading history in a lot more detail with gravity and aeromagnetic maps. We now know the age of the thick salt deposits in the Gulf of Mexico, both in Campeche and also up in the United States, and also in the Burgos Basin of Mexico. We have improved some of the plate kinematic constraints on the separation of North America and South America. I won't talk very much about this, but we have made an important improvement there. We have also done a lot of field work in the Quiqueteco belt. This is the Sierra Juarez down south, and the Jaltepetongo and Chavillas Basin opened up in a certain way, which we will discuss, and that helps us understand the evolution of southern Mexico. And we have also realized that there is a lot of exhumation of very, very deep crust with Permian and Triassic anatectic granites. And the extension involved with this uplift and exhumation was so strong that it made the crust end up only half as thick as it had been. And that helps us understand a very important problem between North America and South America, as we will explain. And then also the crustal extension in Western Florida has been very large. We won't talk about this, but the extension in Florida is also important to the understanding of the whole region. Okay, so here is a map. It's a complicated map. It has a lot of information on. Some of the main things to pay attention to are that there is a big fault down the axis of Florida. And on the west side of this fault, we have a basin called the Mississippi Salt Basin. And then there's the Wiggins Arch, which is a basement high. Then we have another basin, which is a low, then another arch, which is a high, and then another low, and another high, and another low. So during rifting, all of these highs and lows were stretched out, and now they are occurring farther apart than they used to. So there's a lot of extension taking place in Florida in here, and that's what I was talking about. Okay, in the Gulf of Mexico, we have two colors. You see a yellow color, both in the north and in the south. That is the area of salt deposition. There is a thick halite unit called the Luan Formation in the north, or the Campeche or the Sureste salt in the south. In between the two salt units is the area of oceanic crust in the Gulf of Mexico. And we believe now that this dashed line outlines the area of ocean crust very accurately. And along eastern Mexico, the ocean crust comes very close to the coastline. And in the Veracruz Basin, the oceanic crust goes beneath the onshore portion of the basin. In the area of ocean crust, there seems to be two phases of seafloor spreading with a slightly different orientation. And that's the difference in these two colors that you see here. Okay, and then in onshore Mexico, there are a number of very important structures. One of the main ones is this gray dashed line. All of the basement to the left or to the west of that line is composed of island arcs or continental arcs, which have been accreted to Western Mexico or built upon Western Mexico. And then the eastern part, with all the colors and the faults, this is all continental crust. And the faults all tend to be northwest, southeast, and they isolate basement highs, which all have different names. This one's Coahuila, here's Tamaulipas, this is Tuxpan, there's another one in here, Santa Ana. Okay, there are also some basins shown in here. Here's the Huayacocatla embayment, so on and so forth. But there's a lot of basement highs separated by southeast trending faults. And we think these are all extensional faults. And we think that they also have some strike slip movement on them of a left lateral nature. And so we will talk about how all of that works. Okay, I think that is enough introduction with this map. So let's move on. We'll talk first about the oceanic crust, because that's the most important thing. This is a gravity map from a 2014 paper, and it shows the vertical derivative of the gravity. And what you can see for the first time in 2014, you can see the shape of the old spreading center going down the Gulf of Mexico. Does everybody see that? You can see that dark outline of what the seafloor spreading center used to look like. Now, the reason we can see it in gravity is because what is left at the seafloor, at the basement, at the top of basement, there is still the axial valley frozen into the rock architecture at the end of seafloor spreading. And the axial valley has filled up with sediment. So it appears as a gravity low in this image, but it lets us map what the spreading ridge used to look like. And you can see that it's curved. The transforms are a little bit curved, and they all point to a pole of rotation over here. And a pole of rotation, when you're describing a plate motion, is like putting your finger on a piece of paper and then moving the paper around your finger. So if we pretend that the Earth was flat, you could take the Yucatan side of the Gulf of Mexico, you could put your piece of paper up there, and you could hold your finger there, and you could rotate Yucatan back toward North America. And that is called a plate rotation. And that lets us reconstruct what the geography used to look like during the evolution of continents or ocean basins. Okay, so we know what the ridge used to look like. Now we can look at magnetic data. This is magnetic data from an aeromagnetic survey that Pemex shot across the Gulf of Mexico. And it generally is dark colors, but there are three trends across this map. The first one is underneath all the black lines, and you can see the brighter colors, okay? And you can see that all the form lines in the colors are basically parallel to my black segments. This is the magnetic expression of a seafloor spreading ridge, and we can still see it in the aeromagnetic data today. And this black set of lines agrees with the gravity. This is the same as those lines there. Now the blue lines to the north and south, these outline another set of bright colors in the magnetic map. And you can see that in the north, and you can also see it in the south. And if you just try to draw straight lines through each of those orthogonal shapes, you will be able to do what I have done and draw a paleo ridge form on the north and south. So we have to figure out what that anomaly means, and we have to figure out what this anomaly means. We know what the one in the middle means. This is where the seafloor spreading died. So a hypothesis might be is that these ones are where the seafloor spreading started. So let's look at some seismic lines to try to see if we can see what the basement is doing underneath these two outer magnetic anomalies. Okay, here's one from the northern side, and you can see this magnetic anomaly right here, and then it steps over, and then it steps to this one, and then it goes there, and then it goes there, and then it steps again. So these are the little lines I was drawing. But this seismic line crosses this magnetic anomaly. And what you can see is that the magnetic anomaly is marking the edge of the oceanic crust. Okay, it's all oceanic crust out in the middle, and the oceanic crust comes right to this magnetic anomaly. So the magnetic anomaly occurs on the shoulder of the edge of the ocean crust. And then landward from there, in this bright red magnetic color, we have the rifted continental basement, and we have some rift geology, and then we have the salt layer. BSU means the base of the salt unconformity, and the deformation in the salt is clearly visible above that horizon. Now note that the salt comes out to the edge of the oceanic crust, but the salt does not go onto the oceanic crust. On the south side, we have the same thing. Here is one of our southern anomalies and a seismic line across there from Miranda Canseco. It looks like this. Here comes the salt. There's the deforming salt in here. And again, the salt comes to the edge of the oceanic crust, but it doesn't go very far onto the oceanic crust. And there are other places around the world. This is from Morocco, offshore Morocco. Here's Morocco. And this blue line is supposed to be the edge of the oceanic crust. And this black line is the seismic line position. And you can see that the blue line, again, is marking the edge of the oceanic crust before the basement goes down underneath the salt, just like these other places. So sometimes in a lot of ocean basins, you get a magnetic anomaly defining the edge of the oceanic crust. Okay, let's look at some seismic lines in more detail now. This is the same line actually that I just showed you, but it now shows a lot more geology going back landward. We have the oceanic crust. This is the oceanic crust here. Then we can see some faulting in the basement. And then we see a bunch of layered reflectors. And these are the syn rift sediments along with basalt flows interbedded with the syn rift sediments. And then the salt layer lies up here, and you can have, it has basically a flat bottom until you get right out to the edge, and then it starts to get faulted up a little bit more. But the continental crust gets thicker and thicker and thicker, and you go back underneath the shelf areas, and the continental crust is full thickness continental crust. It's about 30 to 35 kilometers thick. So a rifted margin is the transition from thick continental crust through thinner continental crust, and eventually the crust gets so thin that the mantle breaks up to the surface, and you start to get intrusion through the mantle and into the mantle, and that is what starts to form the oceanic crust. Okay, on the south side in Yucatan, this is on northwest Yucatan now, we have the same structure. Here's the moho, or the base of the crust, and this is nearly full thickness continental crust, about 30 kilometers. And then the crust gets thinner and thinner and thinner until it goes to zero, and then the oceanic crust takes over. And above all the basement faults, we have a syn rift section, and then we have some prograding sandy fluvial section, and then the base of the salt is right there in that blue line. And there's not very much salt in this position, and it makes just a little bit of deformation above that blue line. But that is a world-class depiction of what a passive margin looks like. And this is from the ion type of data, which is about the best in the world. On the western side of the Gulf of Mexico, offshore Tuxpan, all of the seismic lines look like this. If you only saw the top half, you would think, well, that looks pretty similar to what we've been looking at. We have a faulted basement, and it gets deeper and deeper, and then we switch to the oceanic crust. And you can see that the oceanic crust has pancake type or layered stratigraphy on top of it, and there's no faulting in the sediments at all. But what the ion data tells us is that rather than the crust getting thinner and thinner toward the ocean, along eastern Mexico, it remains full thickness crust until you're very close to the edge of the oceanic crust. So this is a different kind of margin. This is a transform margin where Yucatan was allowed to slide to the south relative to Mexico during the opening of the Gulf of Mexico. So on the north side, we have a rifted margin. On the south side, we have a rifted margin. And on the western side, we have a transform margin. And when you take off all of the sediments, and when you take the weight of the sediments off, or the mass of the sediments off, then the basement will rebound upwards. And when you allow for the thermal subsidence of the oceanic crust also, you will be able to calculate that the oceanic crust rebounds all the way back toward the surface, leaving only about 2 or 3 kilometers water depth at the time the oceanic crust was formed. And this crust will also rebound up to the surface as well. So during the Jurassic, when the Gulf of Mexico was opening, the eastern margin of Mexico looked like that. And then with the thermal subsidence and also getting buried by all the sediments, the whole thing has subsided, and it looks like it droops over like this. And that's what we see today in the seismic sections. But this is a very good record of a transform type of plate boundary. Okay, now, if it's a transform type of plate boundary, Yucatan must have been migrating to the south. So we have to have a fault zone crossing Mexico between mainland Mexico and the Yucatan part. And that's what this line says. Here comes the transform. This is where it goes onshore in the Veracruz Basin. And then down here where we can see the basement rocks, we have been able to show that the transform goes along what Roberto Molina Garza called the Petapa Fault. And that is to the west of Mixtequita, and it's to the east of the Quicoteco Belt, or the Sierra Juarez. Then it goes across the Isthmus of Tehuantepec, and there it gets buried underneath something called the Chontal Clip. And this is something that was emplaced onto the Mexican margin back in the Paleocene, Eocene. So we're not going to worry about that in this talk. Now, when we go back to our magnetic map, we have the northern magnetic anomaly in black, and we have the southern magnetic anomaly in black. And to make a reconstruction between Yucatan and Texas, what I did was copied the geometry of the southern one, and then I changed it to a red marker color and made it fat. And then I compared them to see if they look similar. And you can see that they look very similar. They can lay on top of each other very well. That means that this once used to be connected to that. And we told ourselves that this is the edge of the oceanic crust. So we now know that all of the crust between these two lines is composed of oceanic crust, right? So we can find a pole of rotation which allows us to move this shape up to that shape. And that pole of rotation lies on the western coastline of Cuba. So if I took a piece of paper and traced the Yucatan block and all of these lines, and I put my finger on the paper here and then spun the paper back up toward North America, keeping my finger fixed on this point, then all of these lines would end up lying on top of those lines. And we would make a plate reconstruction that has removed all of the oceanic crust between Yucatan and Texas. So that's pretty exciting. And I think for an undergraduate, I would think that that would be a very exciting thing to learn. And maybe you have already learned it in classes, but this is the example that we can apply to the Gulf of Mexico. So what that does, when we make the reconstruction, this is what it looks like. So here's present day Yucatan in gray. And when we make the rotation and close down that ocean crust, here's those two shapes again. This is where the Yucatan block belongs. Okay. Now, we also said that the salt goes out to the edge of the oceanic crust, but it doesn't go onto the oceanic crust. So by making this reconstruction, we are also making a salt reconstruction between the north and the south. And back when the salt was deposited, the Gulf of Mexico had a big salt basin across it, and it was all in one piece, one big salt deposit. And then when seafloor spreading started, the two salt deposits got separated by the formation of the oceanic crust, and the Chiapas and the Campeche salt migrated down to here, where it is today. So we need to know the age of the salt. People always have thought it was Colombian for a long time, but now we know it's older. So what can we say about the age of the salt? We collected samples from a whole bunch of places around the Gulf. We went to the Bacab well near Cantarell, and we went to the Espino well in Veracruz Basin, and we got some from the Hockley salt mine, and so on and forth. And then we dated the salt to determine what the age was. And the way we determine the age of salt is with strontium dating. There is a strontium ratio curve that applies to the whole world right through the entire Phanerozoic. And this chart shows the strontium ratio curve between 135 million years and 175 million years. The strontium ratio curve is the ratio between strontium-87 and strontium-86. And that ratio changes through geological time. And lots of people take lots of measurements on chemical precipitated rocks, either limestone or salt or things like that. Anhydrite is another one you can use, and you measure the ratio in the laboratory, and then you can, if you know the age of your rock, you can then help figure out what the shape of this curve looks like. But if you're trying to date a different rock, then you need to take that as a given, do your measuring, and then find out where your ratio crosses the strontium curve. In the case of the Upper Jurassic, middle to Upper Jurassic, there are always two answers because there's a dip in the strontium value at that time. So for this sample right here, this halite sample from Veracruz, the age could be 169 or the age could be 146. Okay, we know that the Gulf of Mexico was already open marine deposition by that time. That's in the Tithonian. That's the time of all Mexico's good source rocks. So that would not be a very likely time for evaporite deposition to be forming. So we know that the age of the salt is this one. And up at Hockley Dome near Houston, we know it's this one and not that one. And at Bacab, we know it's this one and not that one. Okay, so we now know that this salt, in almost all cases, the salt is Bajocian. It's about 169 million years. And there are a couple of weird ones. This one was from Trinidad, so that's not Gulf of Mexico at all. But we had another age in the Veracruz Basin, which is hard to explain. But all the other ones are 169. So we now know that this map is 169 million years old. This is what the Gulf of Mexico looked like 169 million years ago in the Bajocian Bathonian. So that's pretty neat. And now, so that gets rid of the oceanic crust, and now we have to worry about the closure of the continental stretching or rifting that took place before that. And to help do that, we need to know where South America was with respect to North America through time. The Caribbean plate sits between North America and South America, and the Caribbean plate is also moving. So we cannot use the fracture zones or magnetic anomalies across the Caribbean plate to reconstruct North America and South America, or the opening history between North America and South America. What we have to do, we have to define Africa as a reference frame, and then we can close down the South Atlantic Ocean in increments to different magnetic anomalies. But you can see the fracture zones, you can see which are the flow lines that the continents opened along. So we can make a reconstruction between Africa and South America for any time we want. We can do the same thing for North America and Africa, and you can see the fracture zones there as well. And all of these fracture zones are crossed by magnetic anomalies. So all you have to do is choose the same magnetic anomaly on either side of today's spreading ridge, and you can make an accurate reconstruction in both of these oceans. So if you wanted to make a 50 million year old reconstruction, you could choose a magnetic anomaly that has an age of 50 million years, and you'd have to close the North Atlantic down to 50 million years, and you have to close the South Atlantic down to 50 million years, and you will end up with a narrow looking Atlantic. But the relationship between North America and Africa will also change because these are closing in different directions. North America and Africa will be much closer together 50 million years than they are today. Okay, so let's just look at the results of this type of analysis to keep it simple. Let's ignore the black line for now. That's an old relative motion history that we don't use anymore. We use the blue one because of some of the improvements we made. And this is where, okay, we're trying to track this motion of South America. It's near Caracas, back through time. So at 195 million years ago, this is at the end of the Triassic and the start of the Jurassic. This is where Caracas was, pretty close to Northeast Mexico. but then Caracas has moved like this during the opening of the Atlantic. So that lets us plot in all these blue lines where South America was at all these different times. And that gives us the framework for trying to figure out the evolution of the Gulf of Mexico. Because you can't put the Yucatan block on top of Venezuela, and you can't put the Yucatan block on top of Mexico or Texas. You have to keep the different pieces of continental crust next to each other and not on top of each other. So that's how we do that. There's one more important thing we need to worry about, and that is the deformation which has happened in the northern Andes. I won't talk about this very much at all, but the present day coastline is in the fine black line that you can see here. There's Perajuana and Guajira and Santa Marta, and Panama is over here in the Sinu belt. But there are lots of big fault zones crossing the northern Andes. And we can cut the geological map up and try to restore these different blocks by the amount that they have been offset next to their neighbors. And when you do this all together, you can get a reconstruction that should look more like what South America looked like prior to the Andean orogeny. So this type of work is called making a palinspastic reconstruction. It just means trying to unravel some of the deformation that has happened. So what we're left with out of all of this is, here's the full closure position of South America in the blue line. And then this heavier blue line is the shape of the northern Andes that we just looked at. And then Mexico has continental crust all the way down to the red area, this red line. And then it also has additional crust in the Oaxaca block to the south of Quiqueteco, which is shown in yellow. In the pink or purple color here is the Trans-Mexican Volcanic Belt, and west of this gray dashed line are rocks that did not exist in the Triassic or Lower Jurassic. So we don't have to worry about that. But we do have this area of crustal overlap between South America and southern Mexico, and we have to figure out how to avoid that. One hypothesis is that there was a Mojave Sonora megashear, or a big transform, that came across northern Mexico, and it allowed all of this crust to move in that direction from up here. But the people who are trying to define this structure are not having very much luck, and not very many people believe in that anymore. So we need to look for different explanations. So let's worry about the Oaxaca block at first, and I'll tell you about some of the work we did in southern Mexico. Here is the Sierra Juarez, or the Quiqueteco belt, down to the south of Mexico City. There's Puebla, okay, Veracruz off to the east, and Oaxaca down to the south. Okay, we did a lot of work in here, and what we know is that there is a deep water collection of sediments, Cretaceous sediments, which are folded and thrusted to the east up on top of the Sierra Juarez. And those are in the green color. The brown is basement, and this deep gray or steel gray color over here, this is also basement, but this is a special kind of basement. It's a myelinite belt that a lot of different people have worked on. Alanis for one, and we'll talk about that in a moment. But first of all, let's think about the shortening and the folding and the thrusting in the Cretaceous section. Here is a cross section that we made. This is by Rod Graham in his paper just 1 year ago. Up on top of the Quiqueteco and in the Sierra Juarez, we have a lot of folded and thrusted Cretaceous section. When you try to take out all of the shortening and pull back all of these pieces off of the next one, it all has to be stretched out back to the west. Okay, so when you do that, there is so much shortening up in this fold thrust belt that it all needs to be pulled back. And it turns out that there's about 50 to 70 kilometers of shortening responsible in the creation of the present day geology. So when you restore that and pull it back, the Oaxaca block has to move back by, let's say, 50 kilometers back to the west. Well, what happens is that a lot of this deep water sedimentation up on top of the mountain belt gets pulled off of the top and restored back into what was a basin with very thin crust. Okay, we call that the Chavías Basin. And then when shortening turned on, and this would be the Laramide event, active from about 90 to say 45 million years, the Oaxaca block migrated back toward the basement of Quiqueteco, and it pushed all of these sediments back up on top of the Quiqueteco basement. Okay, now this is a field photo of that special belt, this one right here. Okay, what we see, this is a myelinite, and a myelinite is a foliated rock, but all the foliations have stretched out minerals in the foliation. And I think you can see that in some of these places. It's down to the left and it's in the foliation plane. And this foliation plane tilts to the west or dips to the west at about 30 to 40 degrees, depending on where you are. All right, I won't go into this very long, but this is basically, you're looking into a fault zone here because all of these surfaces have these striations on it. And what it means is that the rock moved parallel to the striations, and the slip planes, the planes that the slip took place along is the foliation. Okay, so in order to describe the data we collected, we can look at a very simple block diagram where this might have been the situation before the fault zone was made, but the foliations point basically to the south, and the the striations, or the lineations, point basically to the south, and the foliation dips west. So the top of this fault zone is shown in blue, and it has moved south, and it has been extensional with respect to what underlies it. Okay, I hope you can see what I'm trying to draw. In addition, we can date rocks which have been affected by this myelinitization, and they come as young as 131 million years. So we know that this was happening from, say, Middle Jurassic time up to the earliest Cretaceous by the various ages which have been reported in the history. So Alinus Alvarez started this off, and there's been other people, and we got these younger ages at 132, 131. So we know that this process is happening for a long time. So in order to reconstruct this basin, we have to do two things. We have to move the Oaxaca block back to the northwest to account for the myelinites, and we can move them as far as we want because there is no offset marker. The other thing we have to do is account for the shortening. So we have to move Oaxaca block away from the Quiqueteco basement in order to have a deep water trough. This is the Jaltepetongo Chavías Basin between those two basements. So we think this is what the basement looked like in the early Cretaceous after the opening of the Gulf of Mexico. Okay, and then at the onset of the Laramide shortening in the upper Cretaceous to Eocene, here's our basin. At the start, we have to start the shortening. So Oaxaca block is going to start to migrate to the east, and then some of these thrusts will propagate up through the sedimentary section to form the folds and thrusts that we see up on top of the Quiqueteco belt. We think that the Oaxaca block was in place right up onto the top, but then it has been down dropped after the Laramide orogeny by late and brittle normal fault motion on the Oaxaca fault sensu stricto. Okay, so what this means is that if we back up one slide, we can push Oaxaca back to the northwest by some distance in order to help avoid the overlap with Colombia when we close the oceans. Okay, that's why this is so important. The other thing we can do is look at the area that I call Peninsular Mexico, which is up here. And this is the area with all those faults and little slivers of continental crust, the Tamaulipas Arch and Tuxpan and Santa Ana, and so on and so forth. And then Quicoteco sits down here. So all the way down to Quicoteco, it looks like we have continental crust, or this set of blocks. But as we said, the types of geology at the surface underneath the sedimentary section, which often includes Jurassic marine strata, or sometimes Triassic or lower Jurassic red beds, continental strata, or sometimes it's just the evaporites itself sitting on the basement. The types of rocks we see right under that unconformity are the types of geology that you would expect at 10 to 15 kilometers depth in the crust. So somehow those basement rocks, those mid-basement or mid-crustal rocks, were raised and elevated to the surface before deposition even began. So let's look at possible processes for how that can happen. Crustal extension is almost certainly involved. And it turns out that you need about 100% crustal extension in order to expose the middle part of the crust. Well, in order to have 100% extension, we have to have about 100% thinning, or the thinning needs to take a thick crust down to about 50% of what it actually was at the start. So we can change the cross-sectional volume of the crust by pushing this back to the left and thickening the crust in order to maintain the original volume in the cross-section. And when you do that, there might be 2 generations of faulting, but this is one way to bring some of this crust back up on top of these mid-crustal intrusions. So the hypothesis here is that Mexico's crust was once much thicker and only half as large as it is today. Well, if that's true, then we can draw a map that cuts down the area of our Peninsular Mexico to about half of its mapped area of today and restore that to an area that's half as large. Well, we're very lucky because what that lets us do is avoid the overlap with Mexico, with Colombia. So if we went back to this map, we can unstretch, or we can push all this crust back up into this area, and we can avoid the overlap with Colombia and Western Venezuela, okay? So that's why this is important. We have to be able to avoid that continental overlap, and this is one way to do it. Okay, so now let's look at the age of this faulting that we were just talking about. All of these faults that we're talking about, making accommodation space for the sedimentation, which would eventually bury that basement. These faults appear to come up into Oxfordian, Kimmeridgian, and sometimes even Tithonian time. So basically the faulting in onshore Mexico is continuing right through, let's say, late Triassic, through early Jurassic, through middle Jurassic, and into most of the late Jurassic. So there is a big, long stretching history, 60 or 70 million years. And it's during that stretching history of the basement crust that we believe what is responsible for elevation of the mid-crustal plutons to the depositional surface. Okay, just before we run through our evolutionary maps, there's one other map I want to show, and this is the depth to the base of the salt or the top of the oceanic crust around the Gulf. Our black line here outlines the oceanic area. This is the area of oceanic crust where we know seafloor spreading took place, but you can see that the deep areas in blue and green on both margins, these are places where the continental crust has been greatly thinned by the continental rifting. And it's getting thinner and thinner as you approach the edge of the oceanic crust. So we need to have a means of explaining all of this thinning and the creation of some of these horsts and grabens along the western side of Mexico. So trying to reproduce this part of this map outside of the oceanic crust, that will be our stage 1 northwest southeast extension between North America and Gondwana. And then the stage 2 rotation of Yucatan will form the oceanic crust between the rifted margins, right? So that's just the same as this, our very first slide. We have to stretch this northwest southeast, and that creates something like this. And then we have to rotate Yucatan while South America continues to move away farther. Okay, so here's the end of the Triassic and the start of the Jurassic 195 million years ago. Here's the African coastline. Here's the South American coastline. Here's our reconstructed northern Andes. Here is our restored thick area of continental crust in northern Mexico. We've had to push the Oaxaca block all the way from down here, all the way up there in order to avoid overlap with Colombia. There is a hole that remains in here, and that's where the Yucatan block has to be pushed, and it ends up sitting very tightly against the Texas-Louisiana coast. We have also shortened the length of the Florida horsts and grabens, and we've tightened all that up to form an area of full thickness continental crust. So at this time, this whole region was probably very thick crust, at least 30 kilometers. We don't know of any marine basins at that age. And the crust in northern Mexico was even thicker, maybe even 50 kilometers thick. Okay, so some cartoons. The next map will show 177 million years. So South America and Africa will pull away, and you will see Yucatan move from up here down to here. So now we're starting to form a gap between North America and Yucatan. And we also have rifting between Trinidad and Venezuela and Eastern Yucatan. We're stretching this area in here, and Oaxaca is following South America without forming a basin between them. The next map will be 167 million years, and that is the age of the Salt Basin. So that's what the Salt Basin looked like about in Bethonian time, prior to the onset of seafloor spreading. Mexico has stretched a lot more by this time, but it still has to stretch farther. Oaxaca has migrated down to this position, but it still has farther to go. Florida has also stretched out, and it's possible that the stretching there has now been finished. We can see a broad basin forming, and now the ocean is getting in, probably across Mexico, and the water is in a shallow basin here, and it's evaporating, and it's depositing salt. So as the evaporation proceeds and the water leaves, we end up precipitating salt across the basin, and the water has to be replaced with new water, new oceanic water that drops its salt, and then that water evaporates, and so more water comes in, and it's just a continuous arrival of new salt and evaporation, and we deposit kilometers thickness of salt across most of this basin. It's really amazing. There's also rifting along eastern Yucatan and northern Venezuela. And then in the next map, this dashed line is going to be where the seafloor spreading starts. And by the Oxfordian, we have a very narrow oceanic window starting to form, like the Red Sea, between the two salt-bearing rifted margins. We're also probably starting seafloor spreading between Venezuela and Yucatan. Then by the Kimmeridgian, this is the middle part of late Jurassic, 154 million years. the oceanic crust might have been that wide. And you can see here's our pole of rotation, and the spreading is happening around that pole of rotation. And we are forming this eastern transform as this progresses. And the curvature here, this is concentric around the pole of rotation. All of these fracture zones are concentric around the pole of rotation. Okay, by this time, most of the extension in Mexico is finished. The Oaxaca block has probably migrated as far south as it needs to. And now further separation between Oaxaca and Colombia will take place by the formation of a seaway between southern Mexico and Colombia. But Yucatan still has a little bit farther to go. So one more step in the slides, 147. Oop, Yucatan's not quite there yet, has a little bit more to go. But now we're forming what I call the Colombian Marginal Seaway between Oaxaca and Colombia. And then one more increment. Finally, Yucatan can get to its final position without overlapping Colombia. Okay, so we have the Gulf of Mexico. We have the two salt basins. We have the oceanic window between the salt basins. We have started to form the Proto-Caribbean Seaway between Yucatan, the Bahamas, and northern South America. This is not the same crust of today's Caribbean crust. And we've already opened up the Atlantic by that much. And here's the western edge of Africa right there. Okay, so that's the evolution. And we know also that the end of spreading can be mapped in the southeastern portion of the Gulf of Mexico by a seismic line or many seismic lines. This shows that the extensional creation of a basin was finished at the top of the Berriasian, which is the first stage of the Cretaceous. It's about 137 to 140 million years. Above that red surface, there's no more basement extension. So that is the same as saying that the rotation of Yucatan has finished. So we don't have any more extension taking place there. So now from here on, the Gulf of Mexico will get no larger, and all of the extension between North America and South America will take place through the Proto-Caribbean and the Colombian Marginal Seaway. And we have one more reconstruction to show, and it looks like that. So now this basin is getting wider. The Gulf of Mexico has stayed the same. And we have arc systems in the west, which will arrive from the west and start to form the foundations of Western Mexico, Occidental. That's the Guerrero Belt. And down in the Caribbean, this would be the Greater Antilles. And that arc will migrate through time and eventually collide with the Bahamas. So that's a different story, which we don't have time to talk about. But in conclusion, I won't run through conclusions, but to do this kind of work, you have to integrate plate tectonic data, field data, and lab scale work. All of those things have to happen, and you have to integrate them to make regional analysis. The revised evolutionary model provides new ideas for testing at finer scales of work. So lots of student work doing theses to try to test some of these ideas. For example, here are two. Does the Quequeteco belt represent a Jurassic to early Cretaceous zone of mid-crustal sinistral shear with strain partitioning on the high angle faults? We did some more work that I didn't talk about, but this is just a proposal. This is one possible interpretation for Quequeteco. Other people need to go and see if they agree or if they have different ideas. Also, we've proposed a new model, this extension model for Peninsular Mexico. Is that a valid way to avoid overlap with Colombia? This model is only 2 years old. I think people are thinking about it, but it's certainly not proved yet. So it's just ideas for testing. And in geology, in science in general, you can never prove anything. You can only build a hypothesis and then you test it. Sometimes the hypothesis will survive the test, and therefore it starts to gain momentum. And maybe it survives 10 tests, and everybody is feeling very happy. But it only takes one test to fail, and then you have to start over with a new model. And that's part of the reason geology is so fun. So I will stop there. I thank you for your attention. I hope I haven't gone too long, and I hope I have talked clearly enough for people to understand. And if anybody has a question, I'd be happy to try to answer the question. Thank you.
Thank you, James.
So I'm going to stop sharing so you can see me, okay?
Yes, thank you. So I open the microphone if there is some question or comments. Is the time now. I see in the chat, but there is no question. It's a comment about your opinion on the Huayacocotla
Huayacocotla, it's an embayment. Okay. Thank you, Samuel. The Huayacocotla sits within continental crust, but it is a rift. And in the early Jurassic, it was marine. And it was one of the few places where we had marine deposition. But the rift filled up with sediment. And after a while, by the middle Jurassic, it became continental again. And there was no ocean water in it. I think this is one of the big faults that is responsible for the late Triassic to middle Jurassic extension. And so it filled up again, and then salt came onto the basin again, or very nearby, maybe not on it, in the Bathonian, Bajocian or Bathonian. And it became marine a second time as you go up into Colovian and Oxfordian. So it's a place where the Mexican crust thinned quite a lot. Starting from 50 kilometers thick, it went down to about 25. And because it's only 25, then you end up with accommodation on top of that crust so that you can get a marine section deposited on top. And that marine section occurs today in the Sierra Madre Oriental. So that's what I think about Huayacocotla. There was a recent paper by a young woman, I think, with Tim Lowton on the Huayacocotla. I think it only came out this year, so you should try to find that. I can't think of the student's name, but if you wanted to send me an email, I could find it. Okay.
Okay, thank you.
Yeah.
¿Hay alguna otra pregunta, comentario? Es el momento, hay que aprovechar al ponente. A ver.
I have a question.
Please.
I'm
Javier?
Hi.
Hello, Javier. How are you?
Fine, you?
I'm fine as well. I'm glad to hear from you.
Me too. You have a very good information with the seismic. I have a question. When you talk about the Oaxaca block, do you consider both the Oaxaca complex and the Mixteca complex?
Yes.
Okay.
Yes.
What is it? My question is because both blocks have a different Mesozoic history.
Okay.
For instance, in the Oaxaca block, we do not have Jurassic, while in the Mixteca block, we have all the stratigraphic Jurassic section.
Yes.
On the other hand, both blocks, the Oaxaca and the Mixteca blocks, according to some Pemex geologists who have worked in Tlaxiaco and others from the Instituto de Geología,
right?
we consider that there is a big fault. Pemex called that fault Tamazulapa, the Tamazulapa fault,
Okay,
whereas the Instituto call it the Caltepec fault.
right.
On the other hand, east of the Oaxaca block, we have mapped the Tomejin fault. Those maps have been mapped. However, you proposed a fault that goes, that trends almost west-east, not
Yes.
the Oaxaca fault. And
Right.
what evidence
Well,
you have to propose and to not consider the stratigraphy, the difference in stratigraphy,
okay.
because I wonder in your model, what is the origin of the Tlaxiaco Basin?
Okay. And Tlaxiaco, that's on Mixteca, yes?
Yes,
Okay. I think as we head west, we are getting closer to the Pacific margin.
sure.
So it will be more likely to see marine deposits as you head west. So I would suggest that the Oaxaca block was thicker than Mixteca, so that it sat more positive and therefore was higher above sea level. So that would be one way to help keep the marine section off. But also it's farther from the Pacific margin as well. So that is one very simple little answer. As for the faults, because there's rifting in the west, there has to be rifting in the west in order for that back arc basin, the Arperos back arc basin, there was probably, there will be subsidence associated with the formation of that basin. And Mixteca probably felt that and underwent some subsidence, but Oaxaca might not have. Now, as for the faults, I know the model for the Mylonite belt that Alanis came up with, and we tested that. I think in the south, especially toward the south, toward the city of Oaxaca, the Mylonite belt dips to the west, even though the lineations are still north-south. So that indicates that it's a transtensional type of deformation. I realize the Mylonites it's not so clear in the north, and there's more deformation. But in the south, that is fairly consistent. So we went with this left lateral extensional mechanism for forming the Chavías Basin. And we were able to show that rocks as young as 131 million, that's Cretaceous, are affected by the Mylonites. So that deformation event actually lasted longer than the formation of the Gulf of Mexico. And I think that fault zone, as well as the Quicateco in general, I think that is what I call a Cordilleran event and not a Gulf of Mexico event. We're trying to get basement into the area where Colombia had been. That requires left lateral motions along faults. But the migration of Yucatan from the north, that was dextral along eastern Mexico. So I think they're very, very different events. I think they have been confused in the literature a little bit. And in order for the Oaxaca fault to be part of the Gulf of Mexico story, there would have to be an oceanic basin extending from the Gulf of Mexico over to the north end of the Oaxaca Fault, and there isn't one. And I don't think there ever was one. So I have a lot of problems with that model, and that's why we paid so much attention to this in our program. But, you know, as I said, this is just a new model, and it needs to be tested by other people doing different things. So I hope I have answered that well enough. I don't know very much about that fault you mentioned, Caltepec, was it? I don't know much about that. I listened to Eliza Fitz last night. I stayed up till 1 a.m. in the morning here in England, and I listened to Eliza, and she mentioned that that fault was possibly Permian or maybe early Triassic in age.
Yeah,
so
it was reactivated later on.
Did it? I don't know. I don't know. That's an interesting question, and I need to learn more about it. But it sounded to me from her talk last night that the main period of motion that she has been able to date is prior to the opening of the Gulf of Mexico. So it's older.
It's correct.
Okay. Okay.
It was reactivated.
Okay. Thank you. Thank you.
Good to
Okay.
see you.
Yes. Good to see you.
Okay. Is there any other question? ¿Alguna otra pregunta, comentario? Lo pueden poner aquí por chat. I know you made a big effort and succeed in making all these too many million years compressed in 45 minutes. It's a complex evolution, more complex than I thought. And I wonder if there is, what would be the false hypothesis for your model for the next coming years of as a geological challenge?
Well, I think those two main changes, the extension in the basement, that's a very important question. And also the Quicoteco as a shear zone, a transtensional shear zone. Those are the two main changes. There is not very much we can change in the offshore because I think the seismic data is good enough now to map the limits of the ocean. And we know the depth of the base of salt, and the basement in the Gulf of Mexico has not deformed very much. What makes Mexico difficult is all the basement deformation in the Laramide and the Chiapenec, and that's what makes it hard to read back to the Jurassic. So those two big changes in the model, I think, are important. It would also be nice to get more strontium ages on more salt deposits. As far as I know, nobody has dated the Huehuetepec, which is just east of Huayacocotla, I think. And there is a student, I'm trying to think of her name. Oh, she's a really nice lady. I can't think of the name. Anyway, she's been dating the Minas Viejas up north.
Natalia, I think she's in the audience, no?
Oh, fantastic. Anyway, I saw her present in Mexico just before lockdown. It was the last conference I went to, yeah. The last place I've been.
Everybody.
Like you.
Natalia Mezcua.
No, it's a chronostratigraphic marker. Anyway, she presented a talk there, and she had finished the limestone, and she has Bajocian ages, right down to the Bajocian. But she still wanted to do the halite, and I don't know if she's done the halite.
Any comments, Natalia? And I have
Natalia, that's right.
Natalia Amezcua. I guess
she's not here. she's not here because I have a meeting work.
Okay, I talked too long.
Okay, I
No,
have
no.
two more comments. Samuel, I'm sorry. Adelante, Samuel.
Well, Tim, what is your opinion about the age of the Todos Santos formation of Chiapas?
Aha. Hello, Sam. How are you?
Hi.
Well, that's a good question. It's many things. In its type section in Guatemala, it's early Cretaceous. But when people brought it over into Chiapas, it ended up looking like a sin rift deposit, which it is. And so it took on the association with rifting. But in Guatemala, it has nothing to do with rifting. It's just a coastal onlap. So that's interesting. In fact, it's the Todos Santos equivalent that is the reservoir in the new discovery over in Belize. It's the coastal onlap. It's the basal sandstone. Let's see. So the Todos Santos, there's a very good student by Gudinez, worked with Roberto Molina Garza, and they dated some basaltic rocks in the lower portions of Todos Santos, and they got 196. It's the very first stage of the Jurassic, and that is probably Sin Rift. It might relate to the Camp plume episode across the rest of the Atlantic. Hello, I can see you now. And anyway, so the red beds continue. There are active faults in the lower bit, and the upper bit, apparently not so many active faults. So it's the Sin Rift continuing up into the what might be equivalent to the SAG section in offshore seismic sections, like I showed you. As far as I know, there are no lacustrine intervals onshore that I remember learning about. We do, this Guidinez, he did have zircons as young as 170 million years. And he still had more of this Todos Santos above that with no zircons. So it comes right up to the age of the salt, presumably. And then I would guess that the salt overstepped that and onlapped the Todos Santos. But it must be equivalent to the Eagle Mills up in West Texas.
Eagle Mills is lower Jurassic or?
Well, it's late Triassic. It's very poorly dated. It's upper Triassic, dated by 2 leaves. And I think they're over in the east near Alabama, maybe another one in Mississippi. So the dating in the west is not so good, but it does have zircons of Jurassic age. So it does come up into the Jurassic.
Okay. I stayed a couple of years in the Todos Santos formation.
Yeah.
And my opinion is upper Jurassic.
Oh, really?
Because in the Rio Negro section,
yeah,
the red beds are interbedded with limestones in transitional chains of facies to San Ricardo.
Just a minute, Sam, hang on. There you go. I'll be out in a minute. I'm sorry, I had to do something. Go ahead. Okay, in Rio Negro, it's interbedded with limestone. Interesting.
Yes, and the road from I don't remember the towns, but in the way in the road to Rio Negro, the red beds are interbedded, and
okay.
and also is a concord, no uniformity between red beds of Todos los Santos and San Ricardo.
Okay,
It's concordance.
it's concordant. Okay,
Concordance.
okay,
Yes.
right, okay. Huh.
It's
I'll
interesting play for oil and gas because down deep, for me, is a fluvial environment
Yes,
that changed down deep to the Gulf of Mexico to
lacustrine.
lacustrine to marine facies chains, lateral chains. I guess.
Do you have any proof of that?
There are. I have a very little data, but there are wells that produce in Oxfordian, not in the Cantarell area, to south of the Cantarell area. Maybe Javier Meneses is more know much more than me, but I guess it's a Upper Jurassic.
Okay. Yax Balam, is it that coastal section at Yax Balam?
No, it's far away.
Okay,
it's
okay.
to south in the offshore
Okay.
Gulf of Mexico. I guess.
All right. Yeah.
Okay. we
Interesting.
have-
Well, that's one thing. The other thing is the Tawe terrain is so different to the Guerrero terrain. Are two different terrains to north in Sinaloa and Durango, because in Durango we have marine rocks of Alenian age.
Okay. Wow.
No older rocks on Terreno Guerrero.
Okay. Okay. Right. Millennium. That's Lower Jurassic. Yeah.
Lower Jurassic.
Lower Jurassic. Right. Okay. Okay.
Okay, thank you, Samuel. Thanks, Kim.
All right.
There is one more comment here in chat. Is there any paleontological evidence about the seaway between southern Mexico and northern Colombia? By Felipe Torres.
Ooh, well, in Colombia, on the northern end of the Central Cordillera in Colombia, there is something called Morrocoyal Formation, and it has a lower Jurassic age, and it is marine. But it's also on the Pacific margin. So, no, the Seaway, there are those Bajocian marine deposits in southern Mexico that, I think there was probably shallow water across Mixteca. And I thought some of that came into Oaxaca, but Javier says no. He knows better than me. But, and then in Chortis, I didn't talk about the Chortis Block, but I think Chortis Block is attached to southern Oaxaca. And it has something called the El Plan Formation. And I think that goes down to Middle Jurassic. And then there's a metamorphic equivalent of El Plan, or Agua Fria. That's another name for it. But that's slightly metamorphosed, and that can't be dated, but they still think it's the slightly metamorphic equivalent. So I don't know. We have more to learn, lots more to learn.
Yes, indeed.
Plenty to do.
Yes, for the young generations also.
Next generation, not by me.
No, for
not
the
by
young,
me.
I mean, with you I mean, this communication between specialists and the young students
Yeah.
should be closer.
Well, we have frameworks. There are lots of similar models now, and so we know the main history, and now we just need to work out the details.
Yeah, it's a high resolution reconstruction. I am impressed.
And we have to be careful not to argue. We have to work together.
Yeah. Okay.
All right.
I am presenting you the acknowledgement in Spanish and in English. So I give you two as a little.
Thank you.
Memory.
I just took a screenshot.
Great. I will be sending it to you by mail. And when I see you again, I will give you some of the most tasty candies from Linares.
Okay.
The Glorias. And thank you very much.
You're welcome.
For all these wonderful and very nice presented ideas and models of your expertise. Thank you very much.
Thank you very much.
Thank you,
Goodbye,
everybody.
Goodbye.
And goodbye. Have a nice afternoon. Gracias a todos. Hasta luego y muchas gracias por haberse reunido. Gracias. Saludos.
Bye bye.
Muchas gracias. Saludos. Excelente presentación.
Sí, excelente. Gracias, James. Jim. Bye.